Lasers mark the dawning of a new age in technology across the various branches of industry. These include telecommunications, advanced military technologies, and broadcasting. They are used in ophthalmology and surgery. What we see is information revolution that marked the turn of the millennia. POLYUS Research Institute, named after M.F.Stelmakh, is a top Russian laser technologies research center making part of the SHVABE holding within the Russian technologies state corporation ROSTEC. Today, POLYUS plc is synonymous with substantial research infrastructure, new discoveries, know-how, as well as expertise, in-house production facilities, a technopark, and most importantly, top-class skill, trained at POLYUS-sponsored chairs in related universities. Our success is largely due to our people, our professionals, who can switch to new innovative technologies very quickly. We take pride in our three core product lines, namely gas-driven laser gyroscopes, semiconductor lasers, and solid-state lasers. In fact, we are world leaders in terms of some of the products. POLYUS Research Institute, established in 1962, was in 2001 named after M.F.Stelmakh, its founder and first director, who not only was a prominent scientist himself, but also made his institute prominent in world science. Monocrystals are grown from oxide refractories here for further use in a range of laser systems components. Here you can see a crystal grower utilizing Czochralski method. Its main nodes are of zirconium ceramics. This is the crystallizer. We charge the feed over there, hang down the seed crystal, close the crucible and start the process. The crystal grows in an inert medium in pure argon at around 1900 degrees Celsius for 10 to 21 days. Using the Czochralski method is power and money consuming, but it yields perfect optically homogeneous crystals. Only 2 companies in Russia can grow such crystals, POLYUS being the bigger one. Some extra impurities are doped in those crystals, encouraging their special transition properties and making those media fit to yield solid lasers that operate across a number of spectral ranges. The most common one we produce here is neodymium-doped yttrium aluminum garnet, which accounts for some 90% of what we're making. These lasers work in 1 micron near and infrared ranges. They are used in laser pointers all the way up to some really sophisticated devices, like those required for submarines communications. They work in 3 microns range, which is particularly relevant for medical applications. Apart from active components, the Institute also makes crystals for passive Q switches to switch between a laser's transition modes, namely between pulse and continuous radiation. Another application is optic nonlinear crystal products made according to the POLYUS patented technology. Today, the Institute is the world's only producer of lithium niobate electro-optic switches having a wide operating temperature range, as well as composite elements with diffused welding between crystals, which brought about the advent of pumped semiconductor solid-state lasers with their unparalleled qualities. Semiconductor lasers are semiconductor devices designed to convert electric power into a visible signal, in fact, into light. What makes them different is their extreme conversion efficiency, which is higher than in any other lasers available. Semiconductor laser characteristics made them largely applicable in the military-industrial complex. 2 major areas appeared: lasers for open data transmission lines and ones for optic fiber communication lines. New challenges are dealt with by a large team, basically of process engineers, tasked with growing epitaxial structures, forming their own elements with predetermined configuration, applying reflective and anti-reflective coatings, metallizing, laser assembly, measuring and monitoring parameters. They are also working in labs on further improving their characteristics and upgrading the devices. We are in one of the labs of our division. Here we conduct experiments using pioneering test stands that are nowhere to be seen in Russia and perhaps worldwide. We are using them to measure the bandwidth of single-frequency narrowband semiconductor lasers. The bandwidth of visible light, for example in fluorescent or LED bulbs, is worth dozens or even hundreds of nanometers. Consumer lasers, like those in DVD players, have smaller bandwidths by several orders of magnitude, while the lasers we are making are still several orders smaller. This is critical for enhancing stability in order to have a frequency standard of 1 second per dozens of millions of years. This global task is yet to be accomplished. Another key parameter is the life cycle and operating time of the devices, which are supposed to run inside vulnerable spacecraft compartments for 120,000 hours, which is around 15 years. These devices should therefore be highly reliable. So here on this stand, we subject the lasers to a prior burn-in procedure, particularly the microchips, to be mounted on the final devices. To enhance the device's accuracy, the Acousto-Optic Laboratory designs and builds units featuring interaction of light and sound waves inside solids. Correct satellite positioning relies on the time, with a degree of accuracy currently equaling 10 to the power of -14, while the task is to enhance it 100 times. To address the task, the lab has come up with a technique and a system necessary to make the devices required. This version of the system can be operated in a variety of ways to yield different products. Among them, piezoelectric converters that transmit sound waves via a sound duct to interact with the light propagating in quartz crystals. This is a simple acousto-optic switch used in lasers, for example, for laser engraving. This tiny device is designed for GLONASS systems and for high-accuracy clock, more accurate than ones available today. To address the task set by the state authorities in terms of the GLONASS satellite system upgrading and improving accuracy of autonomous navigation systems, the Institute has made a big step forward by creating a platformless inertial navigation system integrating Zeeman laser gyroscopes. The gyroscopes and systems built with them constitute a major laser technologies research and design area as developed by POLYUS.
Лазерный гироскоп – это прибор, который измеряет угловую скорость.
Laser gyroscopes measure angular velocity and rotation angles of their platform. Take a real-life example, an airplane. In fact, it has 3 laser gyroscopes that measure the plane's rotation in a 3D mode, with this rotation data used to control the plane. Laser gyroscopes are among the most high-tech and sophisticated laser devices. It takes accumulated expertise to build them, while giving impetus to new technologies, including nanotechnologies. Here also belong perfectly plane surfaces, sputtering mirror coatings for ideal reflection, which together results in more accurate lasers. This will enable guiding airplanes to any destination without any external navigation devices, as well as making robots capable of executing tasks in remote locations and getting back. Any units or systems making use of optical radiation as information carrier require an emitter and a dedicated device that picks the radiation and extracts information from it. This is the job of photodetectors, designed and built by the Optronics division of POLYUS. This is the most widely used photodetector for laser rangefinders in Russia. No similar ones are produced in this country or elsewhere. Here is one of our new receivers mounting a cooler that brings the photodiode temperature down to -20 degrees, control circuits, processor and test circuits. They are used in cutting-edge airborne systems. One more task that our Optronics division is engaged in is fiber optic communications. Optic fiber is used across a wide range of applications, including TV broadcasting and phone communications, as well as special-purpose ones for the military and secret services, in computer systems and gyroscopes. Fiber optic technologies have contributed into the space industry development. Our main strong point is that we're capable of performing the complete production cycle, from concept via techniques and equipment to assembly, adjustments, and quality control. We have built dozens of devices for a number of civilian and military applications. The main emphasis is placed on laser applications for ground forces. Here belong fire control systems for precision-guided munitions, which are very well known in Russia, CIS, and other countries. Almost all such systems that are used besides Russia in India, China, and Egypt are built with target acquisition devices by POLYUS Research Institute. The current trend is to use precision-guided munitions with systems where target acquisition is not done by an operator, but a drone. And here too, we have certain achievements. The drones, controlled by a head like this one, have proven they can accurately identify a target and guide a missile to destroy it. A laser placed within the head can also determine friend or foe, which is an asset, for about 1/10 of the troops on the ground get killed by friendly fire. Advanced technologies for high-tech applications and IT lasers are all developed by Systema Engineering Center, another division of POLYUS. The center also develops civilian laser applications to be used in rail, air, and road vehicles. These devices determine distance to the vehicle and its speed, while also identifying those which drive too fast. Laser speed cameras are not the same as conventional ones, as they have a very narrow beam pattern, which allows the camera to process each car separately. Here is one of the 3 modules making part of the device that can be installed to scan each line of cars. And this is an altimeter for aircraft, allowing to measure the altitude at several hertz. Most of them are mounted on drones. The engineering center Systema, like other divisions within POLYUS, is continuously engaged in upgrading its products and reaching improved parameters. We believe the future holds such wonderful technologies as robotic applications that can be integrated in unmanned devices or allowed to control some high-tech vehicles for both civilian purposes and in modern warfare. This is our production facility, where ideas become reality. The process starts with a printed board and an assembly. As you can see, it's now empty. And here is the same plate finalizing the product. These sections are freely accessible. But there are rooms you cannot enter even if you're wearing special clothing. Those rooms must be kept perfectly clean. This is essential in high-tech production. The crystals, mirrors reflecting laser beams, the air surrounding nose for laser radiators, the water in which future sensors are perfected, all of that is supposed to stay clean. The water in these baths is more than distilled, it's deionized, which is yet cleaner. It has not more than 1 ion of impurities per 1 billion water molecules. To make such water, the Institute launched an ad hoc project. POLYUS has developed some water treatment facilities for regions with low supply of drinking water, for production companies, office buildings and country houses. The Institute is making use of its de-ironing know-how. We succeeded thanks to our reactor, with which we pioneered a very simple and cheap de-ironing technique that is employed in our simple and cheap water treatment unit. After we removed the iron, the rest was easy. Water treatment is a new activity for POLYUS. And here is another civilian application, medical devices of the TheraPhot series, which have long been used to treat major lesions of organs and tissues. However, these devices utilize LEDs instead of lasers. Their therapeutic applications are less efficient than surgical ones, with extensive use of laser knives. Lasers have also brought ophthalmology up to a new level. POLYUS Research Institute is now focusing on such applications. These are destructor devices. They are used to destroy cords inside the vitreous body of an eye, as well as secondary cataracts. In fact, the same hardware operates in rangefinders and medical lasers. The Institute is planning to build more laser radiation devices to treat eye diseases, particularly glaucoma. This will be a far-reaching activity and a very good device. I believe its advantage is that it's brand new. One such ophthalmology device is being showcased at the stand of SHVABE Holding, comprising major research, production and trade companies within Russia's optoelectronic industry. The laser cluster, rightly dominated by POLYUS Research Institute. POLYUS annually takes part in the exhibition Photonics, World of Lasers and Optics, held at Expo Center in Moscow. Our stands also showcase other core products like crystals, photodetectors, speed cameras. The Institute also participates in the business agenda. Today's discussion is centered around POLYUS Techno Park. This is so far something new to us. We are planning to launch and develop about 20 startups. Our company and division managers could act here as industry partners, with our senior employees working as advisors. A startup mainly implies new ideas, fundamentals of innovations. Innovations plus experience allowed to move forward. POLYUS abounds in both ideas and those who generate them. Young and promising minds are picked while receiving education. We are training our future employees at 2 chairs, the quantum electronics and of optical instruments making. Those students are the people we rely on. Professional careers of future highly skilled employees start at school. Young researchers are picked nationwide at physics and technology schools, at contests arranged for talented youth. The next stage is higher education at Moscow State Technical University, Moscow Engineering Physics Institute, Moscow State University, Moscow Institute of Physics and Technology, Moscow Technological University. The 2 latter ones have POLYUS chairs. The institute also has a postgraduate school and dissertation board. POLYUS Research Institute, named after Mitrofan Stelmakh, today is a half-a-century-long history of major discoveries, achievements and know-how. It is over 1,500 well-trained and highly skilled employees. plus 500 Technopark residents. It is unrivaled technologies and instruments with unique performance capabilities. And it is also new plans and ideas, some of which sound fantastic, as once did the very concept of laser.